Well, welcome everyone, and thank you so much for joining us today for the Grasp and Robotics series. As before, as quick reminders, this and previously recorded talks can be found on our YouTube channel and website. And throughout the talk, please submit your questions using the Q&A button at the bottom of your screen. These will be answered during the Q&A panel at the end of the talk. Without further ado, I'd like to introduce our Grasp faculty host for today's talk, Dr. Mark Gimp, Grasp Lab Director, and Asa Whitney, Professor of the Mechanical Engineering and Applied Mathematics Department here at the University of Pennsylvania. Thank you so much. Enjoy the talk.
Thanks, Gabby. So it's a real pleasure for me to introduce Professor Allison Okamura from Stanford. She got her PhD and MS degree at Stanford, and we overlapped while I got my PhD, so that was a long time ago for me. She's currently a professor back at Stanford. She did a little bit of time at Johns Hopkins as well. I was really lucky to have on my sabbatical about a year ago. It's about a year ago. I spent a lot of time in her lab at Stanford, and I was really impressed. She has a very vibrant group the atmosphere in her group is really great, where they study things like haptics as well as medical robotics, neuromechanics, rehabilitation, soft robotics, all that kind of stuff. And it was really impressive to see. So of course, the COVID hit while I was out there, partly so. It was really awkward. I mean, it wasn't really like I was there, but we were able to do things like shared group meetings between her students and my students, which was really interesting. So anyway, it was very impressive, all the stuff that she's doing. She's currently the editor-in-chief of Robotics and Automation Letters, so RAL. So those of you who are writing papers to IROS and ICRA, she's the one that's running the whole RAL side of things. She is one of the pioneers and one of the major forces in the haptics and medical robotics. She was one of the pioneers of the steerable needle work that's started a whole bunch of people in that area. She's won the 2020 IEEE Engineering in Medicine and Biology Society Technical Achievement Award. Also in 2019, she won the Robotics and Automation Society Distinguished Service Award because she's been doing all these great things. Anyway, so with that, let me let Allison get to her talk.
Great. Thank you so much, Mark. And thanks everyone in the Grasp Lab for inviting me to speak. I've missed visiting UPenn. When I was at Johns Hopkins a while back, I had the opportunity to, just drive up to Philly a number of times, and always really enjoyed my visits. And Mark, also, we miss having you in the lab, both in person and in virtually. So it was such a pleasure to have Mark at Stanford for his sabbatical. So give me a minute to share my screen and get my windows organized. Okay, great. Time check. All right. Thanks everyone for coming. I decided to talk today about wearable haptic devices for ubiquitous communication. As Mark alluded to, there's a number of different types of research going in my lab, some in soft robotics, some in medical robotics, but I figured I've talked about those things quite a bit in some recent presentations. So here I decided to talk about so both the history as well as the latest stuff in terms of the evolution of thinking in my lab about how we translate from haptic devices that are more classic kinesthetic robotic devices that sit on your desktop to wearable devices that stimulate the skin that might be more appropriate for a range of applications, including consumer products to health, and a number of the considerations that are not just in terms of engineering, but also in terms of human neuroscience and perception. So beginning, I want to start by thanking all of the amazing graduate students and postdocs that have contributed to this work. The specific projects I'm going to be talking about today, a lot of this work I would say is due to Heather Culbertson, who's now on the faculty at USC and was of course a UPenn PhD grad at the time working with Catherine Kuchenbecker, as well as much of the work I'll be talking today also had contributions from Kara Nunez, who's a current PhD student finishing in my lab. All right, so what are we interested in when we think about ubiquitous haptic devices or ubiquitous communication? Well, we're interested in creating physical connections between different entities. And one obvious pair of entities, of course, is human-human communication. In COVID-19 times, and even when not, just due to travel and distance, often people would like to communicate, but this is often mediated through channels like Zoom, like we are now, or voice only methods. And lots of research has shown that without physical interactions, these communications can be lacking. So one possibility is we enhance human-human communications with a sense of artificial touch. In addition, there are various human agent communications that we would like to have. So I have an Apple Watch on my wrist, and when I'm using a navigation app on my phone, the watch also will vibrate when I'm supposed to make a turn. And this is useful because it provides some information that doesn't require me to change my focus on the environment around me to some screen. But however, right now, this sort of haptic alert is pretty limited. While my watch vibrates and it tells me that I need to make a turn, it doesn't tell me, or at least I can't perceive any difference right now between having to turn left and turn right. And so if I don't already know which way I need to turn, I need to then change my focus to the screen, which of course takes my eyes off the road. So if we could provide a richer form of communication through the sense of touch, which is a channel that's underutilized in human-computer interfaces, then we might be able to improve safety and sort of human situational awareness and have more streamlined interactions with computer systems. Of course, we're all interested in robots as well. And as robots become more ubiquitous in our environment, there are a number of researchers, of course, who are looking at some of the sort of social aspects. So social human-robot interaction and how do we achieve that? However, much of that is done currently in a non-contact form. And while there are some sort of physical interactions, especially for physically assistive robotics, we'd also like to think of haptics as an information communication channel between humans and robots, both in terms of the human providing input as well as getting feedback from a device. So what is this dream device that you're going to wear that maybe just looks like the little cuff that you see in these drawings, but we have to actually figure out how are we going to design it to provide these types of haptic communications. And as I mentioned earlier, there's of course the sort of electromechanical robotics aspect of how do you design them, and then there's understanding human perception and the neuroscience of that touch interacting with all sorts of other things that we have to do with our bodies. So this is actually a slide I stole long ago from Catherine Kuchenbecker, who you all know well, who's now at Max Planck, where she compares sight and touch. And I think this is a really important comparison to make because we often get the question of, well, why use touch when you can use vision? And here I want to highlight that the senses are very complementary. But I will say this also highlights how challenging it is to create haptic or touch-based displays. So on one hand, sight is centralized. So the eyes are in one place on our head, whereas touch is distributed all over our bodies. The fact that touch is distributed means that we have sort of more potential for feedback in different scenarios than you might have with sight. But it also means that if you wanted to provide a complete tactile virtual experience, you would have to wear this whole haptic suit, which not only is technically difficult to build, but would probably also make you pretty sweaty. So you have to think about how are these devices going to be created. Similarly, sight is broad. I can, if I was standing in a room with you, I would see all of you at once. Whereas touch is very narrow. If I wanted to come over and interact with Mark through the sense of touch, I would have to march over there and poke him. That also means touch is active, whereas sight can be relatively passive. Now, of course, vision researchers will tell you that sight is not passive at all. You have saccades, you have to change focus. Of course, to make sight work really well, it needs to be active. But touch, I would say, is even more so. And touch also has to be physical. And it's possible to have tactile interactions and reactions that don't even reach the level of sort of cognitive processing, whereas in vision, that's usually the case. So for example, in touch, we have reflexes and we have reactions that might kind of turn around at the level of the spinal cord so that we don't even have to think about it, for example, in order to protect ourselves from touching a hot stove. So what do we talk about when we think about scenarios where this touch feedback is lacking? So I gave some examples earlier of scenarios where we might want haptic feedback. If you want sort of more practical, specific examples, less sort of consumer products, there's a number where this is important. You could imagine patients that actually literally lose their sense of touch because they've lost a limb, as in the case of a prosthesis user. And then on the right here, we have a number of environments where you are trying to accomplish some delicate task and you would like to keep a human away from the environment. And that might be because the environment's dangerous, as in the case of demining or in space. And sometimes it's because the scale is off. You want to teleoperate because you don't want to cut a big hole in the patient so the surgeon can put her hands inside. Rather, you'd like to go in through small robotic instruments. But using the robot as this tool to mediate this physical interaction so you can accomplish the task means that the human operator loses their inherent sense of touch. So you have to obviously artificially feed it back. And then finally, there's virtual environments, which starts heading towards consumer products, but is also, of course, important in education and training, more and more so, and of course, entertainment these days. But all of these, especially the top set on the right here, we don't tend to think about using them with sort of mobile wearable devices, but rather with static haptic devices, such as in the case of the Da Vinci surgical system, where there's a master console where the human operator sits, and then the patient side robot might be in the same room, or it could be very far away. All right, so shifting a bit to consumer products, this is a famous drawing from Tom Ego from this well-known physical computing book, where he says that this is how your computers see you, or maybe your smartphone, or maybe your iPad, and it has a very limited view of you as a human and your ability to interact with it. So maybe stereo sound, usually monocular vision, and maybe one or perhaps two fingers for interaction. So if we are to interact more efficiently with these computing devices, we don't want to have our interactions narrowed through the bottleneck of the simple channels that Tom Ego illustrates here. Now, what are the haptic devices that I'm referring to that might enhance these types of interactions? So one of the most famous haptic devices historically has been the Phantom haptic device. Now there was Phantom Premium, now there's Phantom Omni, now I think it's called the Geo Touch Magic, but it's changed hands and companies many times. But this is, this is a roboticist version of haptics. It is a serial linkage device. Actually has a combination of parallel and serial linkages. It has motors within it such that if a human grasps onto the end effector, they can feel force feedback, and it's beautiful. I mean, you can feel these virtual objects. It's very compelling, and one of my favorite things about being in this area of research is giving people lab tours and having them feel virtual objects through a device like this for the first time. The challenge is that these haptic devices are extremely expensive. This Phantom Premium here probably cost at least $30,000. This is nowhere near accessible to basically anyone other than a researcher. And they're heavy and they're not mobile. Like they sit on a desktop, and maybe they're not as big as some of our robots, but they're definitely not something that can be used commonly in the field. So what we're interested in doing is saying, how do we get this experience of feeling compelling haptic feedback, but in environments where people normally operate? And so to this, we go away from this kinesthetic or force feedback where you apply a net force and you have to use relatively large motors to push on the hand. And instead we think about stimulating the skin without stimulating the muscles and making joints move. And this is motivated, the idea that cutaneous sensing alone could be really important by these pretty old experiments done by Roland Johansson. Yeah, if you don't believe me about the age, you can just look at the hair and the outfits in this video. So this is work done in the 70s, some early 80s, where they really identified how important cutaneous sensing in the skin was to everyday manipulation tasks. So on the left, this woman is doing this very simple task of picking up a match and lighting it. I love the comet matches being used here. And in this instance, she does it very, very easily. But then a local anesthetic is applied to the skin in her fingertips. So this is not changing her vision. It's not changing her ability to move. It's not affecting her muscles. The only thing it's doing is deadening the mechanoreceptors embedded in her skin that tell her about the local contact conditions when she manipulates this object. So you can see her now after she's been anesthetized, struggling to pick up a match. Kind of looks like a robot trying to do it, right? when our robots don't have tactile sensing, that's another real difficulty for them in manipulating objects in their environment. Finally, she kind of gets this power grasp onto the match and is able to light it. Eventually, yeah, there we go. So this is showing the importance of cutaneous feedback. And well, I won't get too much into details in the physiology. It's important to know that there are a variety of mechanoreceptors embedded in the skin that contribute to this sense of touch in the skin. There are different types, which are listed below here. There are different depths into the skin, depending on what type of skin you have, whether it's the glabrous, non-hairy skin of the palm of your hand versus the hairy skin in your arms and your back. That changes the density and the frequency and the types of mechanoreceptors that exist. So we need to take this into account when we are designing haptic devices to stimulate the body. So how do we design haptic devices to stimulate the body? Well, starting with things that are completely not wearable and mobile, if we wanted to have both a combination of kinesthetic feedback, like what a Phantom Premium gives, and tactile feedback to provide distributed tactile information onto the skin, one way to think about this is these active surfaces. And I should highlight here, this was work done a few years ago by my PhD student, Andrew Stanley, who was also a UPenn grad, did his undergraduate in this case. And Andrew's work was really interesting, and it took haptics to this its most literal sense, in that rather than trying to really create some kind of haptic illusion through feedback, he was trying to recreate the world that you touch. And so this simulation, sorry, it's lagging a little bit, but hopefully you can still see the video. What the simulation is doing is it's changing the mechanical properties and the shape using silicone rubber, which has cavities in it which are filled with coffee grounds. And when you vacuum the air out of the chambers with the coffee grounds lock together and they can become hard. We also use positive air pressure below and some pneumatic actuators to pull on the nodes between the different cells. And that allows us to change both the shape and the mechanical properties of this surface. And what Andrew was using it for was simulating lumps and bumps that might indicate cancer for sort of hands-on physical medical simulator. And there are lots of other cool ways to do this, as I show on the left, but we think this particle jamming is one of the more sort of elegant and compact ways of making this happen. So as beautiful as this was, and Andrew even built a 100 cell array for which he forever will give me a hard time because it was really hard to build. It is this sort of literal approach to haptics is just not very efficient. And so we need to find better ways of using human haptic illusions in the long term rather than recreating the world that we want to touch. So how do we create haptic illusions? Well, this is work that Heather Culbertson did when she was a postdoc in my lab, where she looked at the idea of using vibrations, not just for alerts, like what you currently have when your cell phone vibrates, it's an alert to bring your attention, but rather to actually use those vibrations to communicate more detailed information. And she noticed that if instead of applying a simple sinusoidal vibration, if you created some very carefully designed waveforms that considered the dynamics of the actuator and the behavior of the skin, that she could kind of hit you hard with a displacement or acceleration in one direction and recover more slowly. And what people would feel is a net tugging sensation. Now, that still could be thought of as somewhat literal in terms of guiding people. You can tug them in different directions and they had to interpret that information. But this created a really unique haptic illusion, which I'll say we don't fully understand yet, which is that people would feel compelled to move in the direction of the tugging. If anyone has ever heard of the hanger illusion, where you put a wire hanger, you open it and you put it on your head and it makes you want to turn your head, it's the same effect, but it's not one that we completely understand. But the cool thing about it is that you can take these relatively cheap small actuators, you can make them holdable or wearable, as shown on the bottom right, and you can compel people to move their bodies in certain directions. So this is a form of information communication that is fairly robust and strong and starts to veer towards the ability of being wearable. But of course, it's completely different from the type of haptic feedback you get from a Phantom Premium or from Andrew Stanley's work that I showed on the previous slide. So while we're talking about vibrations, I did want to take a little bit of a sidetrack onto a really interesting medical application that we're working on using passive tactile stimulation. And this is work being done by my postdoc, Caitlin Syme, where she has already studied the use of vibration on the body for passive learning. She could teach people in her previous PhD thesis at Georgia Tech how to play the piano or how to read Braille and how to interpret new types of information just by training them with vibration feedback. But this is her true passion now, is improving spasticity and poor muscle tone after stroke by using wearable devices that provide this vibration. And again, looking at vibrations means that we are using cheap, small actuators that don't require a lot of power because we have mechanoreceptors embedded in our skin that are particularly sensitive to vibrations. And she's shown that when stroke patients who have trouble moving and trouble perceiving wear these for a few hours a day for 8 weeks, they don't even have to move their bodies. They're just receiving vibration stimulation. Subjects can improve their scores on a known spasticity scale significantly compared to control subjects that just wore a sham device. And like with many things in haptics, we discover these very interesting effects, but we don't fully understand the underlying neuropsychological mechanisms that lead to this kind of recovery. So Caitlin currently has an NIH postdoctoral fellowship that's helping her test a couple specific hypotheses about this, that vibration helps regulate electrophysiology. So this isn't necessarily associated with the brain, but it may actually reduce spasticity just because of the way that the mechanoreceptors are stimulated. And the second has more to do with the sensory motor control loop that exists in the brain. And so there are various ways in which we're trying to tease this apart by testing subjects with different types of stimulation. This research, unfortunately, has been on hold for the last 9 months or so because we have not been able to test stroke patients, but we are about to be getting back to this by switching things that we're going to do in the clinic to things that will become take-home devices for patients. And that's the cool thing about actually going for wearable haptic devices, is being able to pivot and saying, well, while we wanted to test things in the clinic in a more controlled fashion, we actually are designing devices that can be taken home and worn and used there. So while we might not be able to be as completely rigorous as we would like to be in our normal research practices, we actually are designing devices that are relevant for our current situation, where we would like to minimize direct physical contact between us and our subjects, especially when we're thinking about vulnerable subject populations like stroke patients. Okay, so I'm going to move away from vibration, although there are a lot of cool things we can do with vibration. We've been trying to explore, vibration can get annoying over long periods, and people can also desensitize to it. So we've been trying to more literally recreate the tactile sensations that you might get from a kinesthetic device, but removing the net forces that you get from kinesthetic devices. And this is a really nice set of devices designed by my former PhD student, Sam Shore, and then built on by Jake Suhosky. And in these devices, they're essentially like little delta robots that you stick onto your fingertip. And the red tactor that's sort of at the tip of the delta can push on your skin in different degrees of freedom. And while it does squeeze your hand and it pushes your skin in different directions, there's no overall net force on your finger because it's wearable. So it is a tactile or cutaneous device, not a kinesthetic or force feedback device. And although these devices do nothing to prevent, in this video, Sam's fingers from passing right through each other, the fact that he gets this local tactile feedback on the fingertips helps him create the right kind of movements to interact very intuitively with the virtual objects that you can see on the screen. And here he's feeling friction. He also feels the stiffness and the mass of the devices through these 3 degrees of freedom of interaction. My student Sophia now is designing an origami-based, robot origami-based version of these devices in order to miniaturize them and also provide even additional degrees of freedom beyond the basic 3 shown here. So one of the cool things about these fingertip devices, you might wonder, if you don't have net kinesthetic forces pushing back on the hand, you know, how is it that people can actually feel these mechanical properties? Well, they can still feel them because unless the forces are supposed to be very, very high, we actually are more sensitive to the cutaneous sensation than, say, the net force of the weight of the object. So in order to be sure that we weren't kind of priming our subjects to be looking for certain mechanical properties, we would just show them 2 objects, a red object and a green object, and we would say, these 2 are different. What do you think is different about them? And we would have the subjects basically guess. And we found that if we changed the mass, people almost always knew that it was mass that was changed. If we changed the friction, people could identify that. And not everyone we were testing were, engineers or scientists, so they might use other language. They might say, oh, it's more slippery or less slippery, or it's harder to drop. And so we would interpret the mechanical parameter that they were specifying there. Interestingly, stiffness was not as obvious. That is how, what is the F equals kx mechanical property of the object when you squeeze it? And we found that a lot of people actually didn't necessarily think that that was stiffness. But it is interesting that if something has low stiffness, you have to squeeze it harder in order to generate enough friction so it doesn't slip against gravity. And so people sometimes interpret that sort of increase in force movement that they had to apply as mass. So this sort of skin deformation feedback, while we were using it for realism in virtual environments, when we're thinking about communication, realistic virtual environments isn't quite what we're going for, right? If we want to communicate information or provide guidance, this is another path for using this skin deformation feedback. I'll also note that we've decided that wearable is not always the best way to go. For a wearable device to work, you have to be able to don and doff it. It usually has to fit just right. So we've also been looking at what are good designs for holdable devices. And this is a preliminary design where we have a little 2 degree of freedom skin deformation device that goes underneath the fingertip. And we provided navigation cues where we would provide skin deformation in different directions and have people basically guided to targets that they could not see visually. One of the interesting things about this is that we realized we had to do machine learning on people to understand how different people respond to haptic cues. Because it turns out that although with audio feedback, if we tell them to go in a particular direction, people will go right there. When it comes to haptic feedback, there was this sort of curve, and it was a subject-specific curve of responses. And it turns out that people do like to interpret the feedback as telling them to go forward or backward. They tend to not want to veer off to the side. And it's not just how they walk, because with audio feedback, they did go in the right direction. It's how they actually interpret the tactile cues. So we did some learning on various human responses and compared starting from a target over here on the left and going to these gray circles, that if we didn't take into account human specific models for how they reacted to this skin deformation feedback, it would be difficult to steer them walking to a particular target. But we could optimize it based on our model of a human specific response to tactile feedback. And we also wanted to then later try not providing them constant feedback, but only to re-steer them as needed. And that didn't work quite as well, but still better than the naive approach. So the as needed haptic feedback used the optimized approach, but only provided haptic stimulation when they were going too far off from the target. So basically we're generating policies for sort of teleoperating humans using this haptic feedback based on our models of human response. So another point is that if you want to use this sort of skin deformation for haptic guidance, you do have to take into a subject-specific response. In virtual environments, that seems less important because you have other cues like vision and even sound to kind of let you know how you're doing, and people seem to adapt quite well, whereas for guidance, we need to take into account humans. And my recently graduated student, Julie Walker, kind of took this to the next level and added more degrees of freedom. She has 2 fingers now in a holdable device, and each one can stretch in 2 degrees of freedom. And she can even create cues like to tilt by pushing up on one finger and down on the other. And we've also found that if you vibrate these in a particular way, you can get people compelled to move in a particular direction, similar to what we had with the asymmetric vibrations that Heather Culbertson had done. So we're interested in using this to now guide people in much more complex tasks, for example, training them how to do surgery. So I'm going to take another very short detour to mention educational haptics. None of these devices I'm going to show you are wearable or holdable yet, but because they are relatively low weight and not very expensive, we hope that this is a path that we can also get to wearable, more ubiquitous devices. Over the years, for a long time, we worked on haptic paddles and hap kits, low-cost haptic devices that would let you interact with virtual environments. We've gone from 1 degree of freedom to multiple degrees of freedom, trying to build a kind of haptic Legos that people can 3D print and put together in different kinematic configurations. And most recently, we've designed these, they're known as hap caps, little haptic buttons that you can press and get feedback. And we're asking children who are right now in the first grade, so 6 to 7 years old, to touch these devices in different orders in order to solve math problems. And we're finding preliminary results that as we integrate haptic feedback, finger movement, and these math problems, that students are improving their math learning versus control groups. This is a study that we did manage to finish, at least our preliminary study before the pandemic, and we're really excited about the results. And my former PhD student, Melissa Orta Martinez, who's now at Carnegie Mellon, is continuing this work. And as you can imagine, if we can find ways to miniaturize the devices, put them actually on the body, that will probably allow us a lot more freedom for different ways of providing haptic feedback in education. So again, although there's no wearability here yet, that's where we would like to go with educational haptics. So I'm going to end by giving a few examples of wearable haptics applications, not in all of these spaces, but focusing primarily on social touch aspects. But first, I do want to highlight, as we now are really thinking about wearable devices for social touch, that we have some big challenges in moving from haptic devices that are on the fingertips or use the hands to ones that are worn on other parts of the body, particularly here, the arm. So these purple dots are not meant to indicate some kind of disease. They're just there to try to describe the density and distribution of mechanoreceptors. And we have very dense coverage on the fingertips and palm, and less so on the forearm because of the different types of skin in these two locations. So that means if we want to provide haptic feedback to the skin and the arm, we probably need to provide larger amplitude of stimulus, and we need to distribute the stimulus more in order to provide sort of the same degrees of freedom of information. Another challenge that we have, which is a different one, is sort of how haptic feedback is linked with movement. So typically we use active touch. If we want to explore an environment, we move our finger around a surface, and that stimulates the mechanoreceptors in a way that we control. We move the finger at a certain speed, or we move back and forth, and we're actually stimulating our mechanoreceptors in a variety of ways that are kind of optimal for the types of sensing that they do. So these were identified decades ago by Lederman and Klatsky as exploratory procedures that people use. However, on other parts of the body, what we typically do is we experience passive touch. We don't really take our arms and rub them over things to learn about them, partly because we have fewer mechanoreceptors there, but also just because our bodies are not built that way. In addition to manipulation, our hands are also built for exploration. And so we have this sort of funny thing that on other parts of the body, separate from the hand, the touch is kind of passive. It comes to us. It's not really being mediated by our own bodies. So that also reduces our understanding of the haptic feedback. So we don't fully have either of these challenges solved, but you'll see how these can affect the types of results and the types of setups that we have in the upcoming projects. Actually, I'm going to skip over this, I think, for lack of time. I'm just going to skip over this and talk about moving away from the fingertips and how we create devices and evaluate them that are in other parts of the body. So first of all, I'm going to take one that is a direct analogy to this wearable fingertip device that provided skin deformation. And in this case, it's a wrist-worn bracelet, at this point very simple, where you have a couple of tactors that can either push into the wrist, just like we were pushing into the fingertip, or they can provide shear on the wrist, just like we provided shear forces on the skin of the fingertip. And my postdoc, Mine Sarach, she used similar virtual environments to the one you saw Sam Shore using earlier, and with a tracking system was manipulating these virtual blocks in the same way, but now all the haptic feedback was coming back to the wrists. So the cool thing about this is that we found that even with this kind of non-collocated manipulation and haptic feedback, participants could still identify virtual object properties like mass and stiffness and friction. While it's not quite as good, it's definitely not as good as what you can get at the fingertips, we think there are going to be a lot of advantages still to moving to the wrist. One example is augmented reality. We have a grant with a company to develop augmented reality haptic feedback devices where they would like the the clinician trainees to hold, real surgical instruments like the tip of it, the base of a needle, for example, because that's not something that can really be, the tactile experience of doing that can't yet fully be recreated with haptic devices. So if people can still manipulate real tools, but get augmented feedback on the wrist for augmented reality, now we're not just augmenting the vision, we're augmenting the haptics. And we can't put the haptic devices in the same place on the hand as where they're trying to manipulate the physical tools. So this is a little bit in its infancy, but we're really excited about both the applications and also understanding how humans learn and the neuroscience of this non-collocated feedback. That's for virtual environments. The previous slide just showed some, very simple, typical electromechanical actuators, but we're also looking at how do we make these things more wearable, and is there inspiration we can draw from soft robotics? So although I'm not talking much about our soft robotics work today, I'll note that we have been trying to implement soft robotics ideas for wearable haptic devices and using some different approaches. So on the left, we have an approach where we have a single point device of contact, and it moves in multiple directions. So similar to that wearable fingertip device I showed earlier. But also, if we want to take advantage of the large real estate that we have on the skin of the arm, as well as acknowledge that we have a reduced density of mechanoreceptors, we would like to put haptic stimulation over a larger area. But like I mentioned, if we had something always on our skin, maybe it gets a little uncomfortable and sweaty. So we had this kind of crazy idea that what if you had a haptic device that was housed in a bracelet and it grew out of the bracelet like our soft growing robots in a different research project, and therefore distributed different haptic stimulators into different locations on the skin. So we don't yet have a great way in a small form factor to retract this device back into the bracelet when you're done with it, but we do have some cool ideas now for wearable haptic devices that distribute themselves on the body and then repackage themselves afterwards. And this work, as I would say, is also somewhat in its infancy as we explore the capabilities of new soft actuators. Actually, I'm going to skip that. So mostly what I want to talk about, though, is using wearable haptic devices for social touch. This has been kind of especially interesting and fun project as we think about people's physical separation during COVID-19 pandemic. So this is a picture of me, stroking my husband's arm, and this is a very common example of a social touch. It can convey calming, it can convey love, and definitely in medical scenarios, there have been a lot of studies showing that this kind of touch can help reduce blood pressure, help people prepare for difficult medical procedures, and is even useful in rehabilitation. So we're interested in actually recreating this kind of social touch, but we don't want to do it in a literal way. Like, we don't want to have a robot come up and stroke people. We want to say, how do we, instead of creating a robot finger that does this motion or a robot hand that does this motion, how do we have a wearable haptic device that recreates this sensation? And this is where we get to haptic illusions. So when she was a postdoc in my lab, Heather Culbertson created a relatively simple array of these linear voice coil actuators, and found that if you find just the right pattern of stimulation and just the right speed, because if you get it wrong, it doesn't feel good. It feels like a spider creeping up your arm. If you get it right, though, then you feel a smooth transfer of motion, and it doesn't feel like a set of individual stimuli. Rather, it feels like a stroke on your arm. So this was pretty cool. We found that we could get this continuous stroke illusion. People, if they didn't see the device at all, would not realize that there were separate actuators here. And we also developed, this was work of Karen Nunez and Sophia Williams, devices. The second video not working so well. Maybe if I stop the first one. Let's see if this one wants to go. Yeah. So on the bottom video, you have these little rotating devices, not as wearable, but we were interested in seeing if both a combination of skin indentation and local skin slip would actually increase the sensation. It turns out you don't really have to go as far as this bottom example. Probably just the normal skin indentation is enough. But one of the cool things we found with this lower example is that you can actually spread these tactors out quite a bit. You don't need very many, and you don't need a high density to still give this illusion of a continuous stroke. So this continuous stroke illusion, I won't get too into the details, but we, again, have to find just the right timing and just the right delays in order to make this work well. It does wind up feeling very compelling as a stroke. So discovering that we could do this with these relatively distributed tactile sensations on the arm, we embarked on a project that was really understanding social touch from kind of beginning to end. So here, Sophia is wearing a tactile array, a capacitive tactile array sleeve on her arm. And we recorded social touches from a number of pairs of people. Like here, we would tell the toucher, through the sense of touch, tell your partner that you're happy or tell them that you're sad. We went through a various set of emotions that we wanted to communicate. And we mapped what we sensed on this tactile array sleeve to pressure distributions, which we then recreated on these tactile arrays, in this case, a simple 2x4 array. And I won't go into too many details of the results, but here is one example. So we, in this case, did 6 different emotional cues that had to be communicated: attention, happiness, gratitude, calming, love, and sadness. And we had the touchee, the person receiving the touch, now from the device, not from a person, to tell us about both the arousal and valence. This is a classic HCI, human robot interaction set of scales called the sensory mannequin, where their sort of receipt of this of emotion landed on this scale. And it turns out that these actually landed in kind of the correct places compared to how people would rate these from human touches. I'll also note that, almost done here. I'll also note that when we think about communication through touch, we also wanted to both exploit the arms as a place where we can always get feedback, because we don't want to have devices on our hands all the time, and also the increased mechanoreception on the fingertip. So this was a very recently published paper from my PhD student, Sophia, where she had actuators, 2 simple vibration actuators that could be placed on the fingertips or on the arm. And the main idea is that you would put these actuators onto the arm, and they could provide sort of high-level haptic cues. They could provide maybe a simple set of vibration patterns that would let you know that you're getting a phone call, and maybe that it's a specific person, like your mother is calling. And then there would be higher frequency or more detailed information that you might not be able to feel through your arm, but you could feel through your fingertips. So if you laid your fingertips onto the devices, then you would start to feel this more detailed information, and you could say, oh, my mom is calling about signing up for a class. So this is also a project that's in its nascency, but we're really excited about coming up with wearable devices that sort of exploit the tactile perception in different parts of the body, and might be practical for receiving information without having to use other channels like sound and vision. So one of the cool things about haptic feedback is if I was in a meeting with all of you and I wanted to get a message, I could just feel this under the desk, from my arm without interrupting anyone else. And haptic feedback is also typically a private communication channel. Other people who are not wearing the haptic device can't hear or see the same message. Yeah, so with that, I'm going to draw to a close. Again, I want to thank all the amazing students, both current and past, whose work was featured here. had a number of amazing collaborators, not only at Stanford, but at other institutions. And in particular, we had great sponsorship of this work from NSF, Facebook Reality Labs, NIH, Neurosciences Institute, and Department of Defense. So thank you all for your time, and that will be it for me.
That was wonderful, fantastic talk. Super interesting stuff. Lots of really cool things. So I want to, of course, give you a round of applause, a virtual applause. So we are entering our panel phase, and we have two wonderful panelists, two students. Jessica Yin is a first-year PhD student who is working with James Picoul and me, and that's interested in soft robotics. We've also got Maddie McGee, who is a senior in mechanical engineering and also a master's student in bioengineering, who's interested in biomechanics and will actually apply to a PhD program probably in the next year. And so they've got a bunch of interesting questions, and we've got several from the audience as well. I want to just remind the audience, we've got some interesting, there are also, if you see the audience list, there are a couple of people professors from around the world who are attending it that are kind of special. I'd like to give a shout out to them. But Maddie and Jessica, take it away.
Thanks, Mark. Thank you, Allison, also for a really great talk. I think we'll just start with a question from the audience. So from the audience, we have, how is realism in a virtual environment measured? How is it compared to the real sensations of a similar object?
I am so sorry. I just had an interruption from my daughter that needed something for school. Could you repeat that?
Yeah, no worries.
So sorry about that.
That's okay. Yeah, so just starting with a question from the audience, which is, how is realism in a virtual environment measured? And how is it compared to the real sensations of a similar object?
Great question, thanks. And my apologies again. nothing like a 15-year-old's classroom emergency. Yeah, so the realism for a virtual environment is, well, it can be measured in a lot of different ways. So one is to create a sense of realism just by a kind of a survey. So we would do a survey, on a rated scale of 1 to 10, tell me how realistic it is. And that can get to someone's sort of belief in how realistic something is. But there are other ways, for example, to measure performance. So if you can hypothesize that people will perform a certain way in the real world, and if they perform the same way in the virtual world, then that gets to a sense of realism. So I think there are both subjective measures from basically asking people, and then objective measures in terms of measuring performance.
Great, thank you so much. One, just for the talk, and two, for that answer. And based on measuring performance and seeing how people are able to actually interact with what you showed with the fire matching, what do you think are other types of ways to stimulate different types of, sensors? So for example, what are your thoughts on potential multimodal haptic feedback? So rather than just mechanical, also including thermal and anything else of that nature.
Yeah, that's a great question. So for multimodal haptic feedback, actually Marcy O'Malley at Rice University has studied this quite a bit. And so she's looked at like combinations of skin deformation and vibration and squeezing as well. And she found that if you combine different modes of feedback, you can actually increase the information throughput. So there's definitely theories here about information transfer rates. And we also tested that in our arm plus finger project that I mentioned at the end. And if you provide different types of feedback, then yeah, you can get more information through. There, I haven't looked at this, but there have definitely been groups that have been studying combining thermal with other types of haptic feedback, and I think that's pretty effective as well. I I think there is a learning period that people go through when they have to interpret different types of haptic information as well. And another part of this that has not yet been fully studied is what if you provide the haptic feedback on different parts of the body? Sometimes we are trying to put these different types of haptic feedback as close together as possible so that we can integrate them into a single device, but it might actually be more interpretable if you go into different locations.
And then I'll also just ask another question from the audience, which is, so thanks for the interesting talk. Seems like there are two different ways to incorporate haptics into human robotic interaction, which is either mimicking the touch sense or teaching humans to translate the tactile sense into new meaning. What is the difference in design and how does a human know which to expect?
Yeah, that's a great question. So I probably described this as sort of information transfer versus realistic virtual environments. And I do think these have really different purposes. When it comes to trying to realistically generate the feeling from virtual environments, we definitely take inspiration directly from physics. You know, if we know that interaction with objects creates a particular type of sensation, that's the sensation that we're trying to generate. And we might still try to find haptic illusions or tricks, like this example of a social touch stroke, in order to communicate that. So even though a social touch stroke is like an information communication thing, we are trying to make it realistic so that it feels like an actual stroke. So in that case, we are taking inspiration from how people are normally stimulated when they do a task. When it comes to information transfer and measuring information rates, you know, I think you can be a little more creative there. And I think we've just scratched the surface of different things that we can try. There you're not as constrained, but probably one drawback of this lack of constraint is that although we can up an information rate transfer, sometimes we are creating sensations that are actually annoying and not ones that people are going to want to use in the long term. So we might check a box in terms of some measure that we have, but probably something our community has to do better is to say, you know, are these sensations that people really want to receive on a regular basis and how often? And that's a consideration that's going to arise more in the case of information transfer, because realism, we're already trying to create what would naturally occur. I hope that answers that question.
In addition to trying to avoid creating annoying sensations that you just talked about, what do you think are other barriers for more sophisticated haptic devices to start making their way towards consumer mixed reality devices?
Yeah. Power. Both in the sense of battery power, storage of power. You know, I showed some fun pneumatic haptic devices, and I say, oh, they're lightweight, they fit on the arm, you know, this is great. But of course, this thing is attached to an air compressor, which is not wearable at all. And there are definitely people who have been looking into more wearable pneumatic devices, not just for haptics, but also for robots. You know, you want to have mobile robots that operate on pneumatics, but right now, soft robots, for the most part, are not truly mobile because they always have tubes, you know, going off. So on the pneumatic side, yes, that's a huge issue. But of course, even with electromechanical devices, we also have battery issues. And another aspect of the power is basically the actuator. Usually power to weight ratio is what we're concerned with. And if you map out all of these different types of actuators, the coolest one in terms of power to weight ratio, which we would like to use, would be things like shape memory alloys, right? However, they have their own challenges. So shape memory alloys, shape memory metals, they tend to move quite slowly. And you might need to cool them somehow in order to get them to respond. So then they have poor bandwidth. So you have these trade-offs with the different types of actuators, but ultimately we would like actuators that have the sort of amount of force and the bandwidth that we want, but with an extremely large power to weight ratio.
So kind of related to that question, what do you think then of the potential of electrostimulation of either mechanoreceptors or muscles and their potential to reduce like device bulkiness or weight by not requiring like motors?
So did I understand that this is like direct electrical stimulation of the muscles or sensors?
Yes.
Yeah. So that's really interesting. So there's two ways to think about this. One is doing it peripherally on the skin or in the muscles, and the other is directly into the brain. So first on the skin. Well, I guess yeah. In both areas, providing that stimulation, it has been difficult to provide sort of realistic or comfortable sensations. The Rehab Institute of Chicago, now the Shirley Ryan Ability Lab, has done these sensory reinnervation surgeries on patients in order to, say, map part of the skin and the nerves in the skin to a missing limb, for example. And then they can stimulate the skin here. And they can create certain types of sensations when they do that, that surgery and they do that mapping. So it's not just a tingling sensation, but people can feel things like pressure. But then there are other aspects of haptics, which I didn't really talk about today, like proprioception, like knowing where your fingers are in space, which has been really difficult to stimulate peripherally. There's been some success in providing both tactile feedback as well as some kinesthetic and proprioceptive feedback by directly stimulating the brain. There's just been a few experiments done in humans, lots in monkeys, and in the monkeys, they can actually use the information and do tasks, but you can't really ask them how it feels. But with humans, they have done it a few times now, and people tend to respond that they feel fluttering or tingling sensations and not things that are akin to realistic feedback. So these kinds of stimulations, I agree, they're promising if just in the same way that there have been challenges with pulling information out of the brain. You need to have a physical interface that can last for a long time, not get infected, not have to be replaced. So there's all sorts of biotechnical challenges there, but it's a really promising and interesting area of research. And the slides that I skipped over in my talk were actually related to a project we have in that area where in this case, we are not yet trying to provide stimulation through the brain, but we're seeing if there is a brain-computer interface that's reading out to control, say, a robot arm or a cursor on a screen, we're trying to augment that with actual haptic feedback on the body to see if that actually enhances the user's closed-loop control. But at the moment, of course, the people who are signing up to do these types of studies, it's because they have a real reason to do so. So in our case, it's a spinal cord injury patient, sensation from the neck down, and is able to type and move robots in his environment by thinking. And this is not, of course, something that everyday people can try these days. So I think this is definitely going to go places. But it's a long road, and of course we have to be really careful considering the invasiveness of the procedures.
And playing into robotics and helping people, like also especially virtually now, how much do you think visual and audio effects play into the role of haptic sensors, and how do you draw the line for visual realism in experiments and the tests that you do?
Yeah, that's a great question. So especially in virtual environments, right, your experience is totally a multi-modal, amalgamation of sound, touch, vision. And we, as you can probably tell from the virtual environments I showed, we are not graphics people. We make blocks in environments, and the visual feedback can actually make a big difference how things feel. So when we were doing comparisons of mass, people might have heard of the size weight illusion. If something looks bigger, but and it's the same weight as something that looks smaller, people will think that the smaller thing is heavier when it's really just more dense. And it turns out those same illusions hold for color and shading and the texture that you draw on the object as well. And one funny study even compares male and female Barbie dolls, and the female doll is perceived as actually more dense because it's smaller, and there's also like other things that they controlled for that have to do with like social training. So it's there's all of these things that go into people's perception, and it's really hard to tease apart. So we are not trying in most of our experiments to try to optimize these other senses, but rather doing in the haptic side, at least like an A/B comparison where we keep the vision the same. But it's totally true that if you want to give the best experience possible, you want all of these different sensations to come together.
So another question, I know you touched on this a little bit during your talk, but what are like the differences and subtleties in designing haptic devices for augmented reality versus virtual reality?
Yeah, that's a great question. So augmented reality is newer for us, but we are definitely interested in this. So there's a couple of things. So when you are using augmented reality, you have real objects in your environment. And I'm assuming if you want haptics for augmented reality, it's not just feeling virtual objects, you know, embedded in the real world, because if it was that, it's more like the haptic part is just virtual reality with haptics. But what I'm thinking about when I think about augmented reality for haptics, I'm thinking that there's a real object there, and when I touch it, I want the haptics to kind of add something. So one thing is timing becomes super important, because physically I am going to touch an object, and the haptic device has to also respond and give me any sort of augmented haptics at the same exact time I touch the real object. So this is a huge challenge for tracking the hands and being able to predict contact. And because any sort of hand tracker, no matter how good they're getting, is going to have some delay, and we can feel and respond to tactile sensations very quickly. I have a student, Mike Salvato, who is looking at hand prediction. So you know, someone's approaching an object, especially if they have a hand in a particular configuration that says, hey, I'm about to grasp, grasp lab, I'm about to grasp. And if I can notice that and then predict that, hey, I'm going to touch in 0.2 seconds, then I can prime my electromechanical device to start moving, to get ready to provide that haptic feedback at just the right time, so that we have these simultaneous contacts in the real world in the haptic device. So that's something that we don't really need to worry about so much in virtual environments, but the timing just, we think, has to be spot on for augmented reality. The other thing that I've been thinking about is with augmented reality, you have this opportunity to do redirected targeting. So I'm not sure if anyone has seen this, but redirected walking in virtual environments is really interesting. You want to have someone walk down an infinite hallway. So visually, you just show them that they're walking down a hallway, but like kind of proprioceptively, you steer them a little bit. And so they're actually walking in circles, but they think they're walking down a hallway. So there's a kind of haptic analogy to that called redirected reaching or redirected targeting, where you reach for, here's my physical object, got all kind of props on the desk here. So you reach out for this virtual object, you touch it, and you move it to a new place. And then you move your hand, you reach out again. But in the virtual environment, you now see your hand coming to a different location than where it's actually reaching. And so let's say you have a task like stacking blocks up. What if you only have one block? You can convince someone that they're stacking multiple blocks when they're only stacking the same block over and over again, because graphically and proprioceptively, you're sort of steering them to think something different. So we're thinking about how do you use this kind of redirection and these perceptual tricks that you can play in both virtual and augmented reality. With the block stacking thing, you have a physical block, so that's the physical reality that's there, which can hopefully provide both a sense of realism and have people accomplish tasks that, you know, don't require that you have 10 blocks physically in your environment. So those are a couple of our ideas for augmented reality.
Wonderful. Thank you everyone for joining us here today. I wanted to say thank you to the panelists and to Mark and Allison as well. For right now, please tune in next week, Friday, February 5th at 11 a.m. Eastern Standard Time to welcome our next speaker, Dr. Jody Ferlisi from CMU. For more information on upcoming events, be sure to follow us on social media and check out our website. Thank you again and have a wonderful day.